This first problem covers conduction, convection, and resistance networks for boiling water in a stainless steel kettle. And we are going to find, with these given dimensions and characteristics of heat provided from the stove, the temperature on the surface of the kettle right after you remove it from heat. So we're going to assume that this is a steady state with the water boiling and that there's constant thermal properties. And we're going to solve a resistance network for that in order to easiest determine that temperature. We will incorporate conduction and convection because for our resistance we're going to need to use the conduction and convection resistance here and here, and we're going to use the area of the bottom of the kettle given. We can arrange that with Q and the temperature difference across that surface and the convection across the conduction over the kettle and the convection into the boiling water over the total resistance related to the heat that is provided. And we're going to rearrange that for that T1 of the surface and come to an answer. This problem covers 4A, the 0D time-only transient heat transfer. We're going to be heating these steel balls from room temperature to a given heat in our boiling water. And we're going to assume these constant thermal properties, and we are going to first find if we can use lumped analysis by finding the BO number here from the corrected length. And because that is less than 0.1, lumped analysis does apply. So therefore, we will go on to use that this temperature relationship is equivalent to e to the negative bt, with b given here and simplified. We can rearrange that for the time and find the time it will take for that ball to warm to the desired temperature. This problem involves transient heat transfer 1D in space as well as a spherical coordinate system, and we are trying to find when ice will melt placed in the sweet tea of a certain temperature. And for this, we are going to assume that the ice is spherical and that this is only 1D heat transfer because it's a sphere and there are constant thermal properties. We're going to look at this with this simplified expression to say when the center of the sphere reaches 0 degrees C, it will be melted. And we are going to find the BO number in order to reference from table 4.2 these lambda and A values, and then along with the characteristic tau, we can combine our equations and rearrange for T, and then solve for T here to find our desired time. This final question covers the deriving a conduction equation with boundary conditions and cylindrical coordinates, because we have this cylinder and we're going to look at the potentially modeling the warming of it in a room, and we're asked to set up the differential equations and the boundary conditions based on our knowledge of the system. So first we'll start with the coordinate system. It's a glass, so we're going to model it as a cylinder, and we're going to say that due to the ratio of the radius and height that we're going to see negligible heat transfer other than on the radial direction. And then from our large differential equations, we will then, using that cylindrical assumption and those equations, simplify down to a starting point for a differential equation. And we can also look at the boundary conditions that would be required to solve that and say we've got a specified convection that we know because we know these temperatures and these heat transfer coefficients. So we can say at the surface this is going to be true, and then we're going to say there's thermal symmetry. So around the center line there's not going to be a change in temperature, and that will come up with our boundary conditions and our differential equations, specifically deriving per the learning outcome.